Hello dear students, today we will try to understand what is called as the gradient drift and the curvature drifts. So far in our discussions about plasma physics, we have been analyzing various types of electric and magnetic fields and how a single particle, a single charged particle with a mass m behaves in these different types of fields. So, we have seen how a uniform and static electric field will influence the charged particle. We also seen how a uniform magnetic field will influence a charged particle, and we also seen a perpendicular electric and magnetic fields, how they will influence the charged particle's trajectory. We have drawn these trajectories, and with this understanding we have moved on to understand to the idea of a varying magnetic field in space, but a static magnetic field. So, in this process we have seen that if the magnetic field is changing or if its strength is changing from one point to another point, we have taken a magnetic field such that its magnetic field strength is lower in a particular region and it is stronger at a particular region. So, we have seen that the main influence of the magnetic field strength changing will come in the terms of its the radius of gyration of the particle. Since we have known that the radius of gyration of a particle is defined as mv by qb. So, if the magnetic field is more, the particle will gyrate in a smaller circular path with a smaller radius and vice versa. So, what we have seen so far is that if the magnetic field is in this configuration such that the magnetic field lines are farther apart towards the negative y axis, let us say. So, the axis that we have taken was such that, so the magnetic field is having a gradient along the y direction and the magnetic field is pointing outwards out of this page, or we can say that the magnetic field is along the z direction. So, in this configuration we have seen that the particle will have a larger gyration radius here and the particle will gyrate in a smaller circle here. So, apart from this, the basic idea was the particle's radius of gyration changes as it moves across the y direction. This leads to the formation, or this leads to the idea of the drift velocity. So, the difference in the radius of gyration as it moves along the positive y direction gives away the what is called as the drift velocity. Fine. So, in this process we made a simple assumption saying that if you define the length of inhomogeneity in the magnetic field with capital L, we have assumed that this length of inhomogeneity must be much greater than the radius of gyration of a single particle. That means what we are trying to do is we are trying to make sure the particle while gyrating in one orbit will not experience any inhomogeneous magnetic field, right. So, having said that, we have tried to expand the magnetic field in a Taylor series expansion. B0 is the magnetic field strength at the center of the gyration, or the center of orbit. Then if it is the case, then we have seen the magnetic field can be expanded as this. So, if the magnetic field is expanded, we neglect all the higher order terms, then we have calculated the average force that the particle experiences along the three directions. Now, since the magnetic field is along the z direction and if the particle is having a velocity Vx, Vy, Vz, the particle will not experience any force due to the magnetic field along the z direction. So, Fz is always 0 and Fx was evaluated to be 0 and Fy was derived to be q v perpendicular RL by 2 dou Bz by dou y. So, I remember having stopped at this point in the last lecture. That means we have derived the average force that a particle experiences as it travels across this gradient or across this non-uniform magnetic field. Now, here what our objective is to find the drift velocity. Let us say we call this as Vf. Is we know that the generalized force will give away drift velocity as F cross B times B square. So here f can be anything. So while discussing the average or the generalized drift velocity, we also said that the role of this f is to give a non-zero velocity to the particle so that it comes under the influence of the magnetic field, right. So if we know Vf is this, we call the drift velocity that arises due to the gradient in the magnetic field as V del B is equals to 1 by q. Since all other components of force are 0, Fy cross B divided by B square, right. So this Fy, the force that is experienced along y direction is obviously along the y direction, that is y cap is the direction, or j cap, and the magnetic field is along the z direction, right. So if you substitute the value of Fy into this equation, we can write 1 by q minus plus q V perpendicular RL by 2 dou Bz by dou y cross times Bz z cap divided by Bz square. So here we have to determine the cross product between y cap and z cap, and Bz being just the magnitude gets cancelled here. So we can write the velocity due to the drift in the magnetic field as minus plus V perpendicular RL divided by 2 Bz into dou Bz by dou y along x cap. So that is the basic idea. So basic idea is you have a magnetic field in this direction. This is Bz and this is z direction. This is the x direction and this is the y direction, right. So the magnetic field gradient is in this direction, the magnetic field is in this direction. Now we are able to see that the velocity of the particles is in this direction. This is the most interesting thing. That means the velocity of the particle, that means the velocity of the particle is perpendicular to B as well as del B, right. So this is the most interesting thing. That means velocity of the particle, so that means the particle is moving in a direction which is perpendicular to both the magnetic field and the gradient of the magnetic field, which is allowing it to move, right. So this is the velocity. So velocity, so now as you see, RL is defined to be mv perpendicular by qb, right. And we also know that the magnetic moment is W perpendicular by B, right. So that means that that means velocity due to the plus minus that we have, velocity is in the positive x cap for electrons and is in the negative x cap for ions. So what does it mean? It means that the gradient, see, we have a very important point. If we look back, if we consider a magnetic field which is homogeneous and static in nature, that means B dou B by dou x is equals to 0. I am trying to make a point based on the particle's movement. So in this situation, which was the first or second particular case that we have discussed, we have seen that both the particles were executing a simple harmonic motion or a circular motion where the x and y components of the velocity were giving you circular motion, right. We have seen that both the particles will gyrate along the same direction, but they will gyrate in opposite direction, in the sense the motion, the circular motion was in the opposite direction. So this is for let's say this is for the ions, and this is for the electrons, and this is, sorry, this is for, yes, this is for the ions, and this is for the electrons. The radius of gyration proportionate to the mass. What we have seen is that both the particles will move in the same direction. Of course, their radius of gyration will be different, or they will more be proportionate to the amount of mass. So that means electron being a lighter particle will have a smaller radius of gyration, whereas the ion being a heavier particle will have a larger radius of gyration. Fine. But one important aspect is that this uniform static magnetic field was not able to create any charge separation. But what you see, when the magnetic field becomes non-uniform or inhomogeneous, what we see is the drift velocity is of course dependent on the charge. That means it is different for, let's say, ion, and it is in the different direction for an electron. That means because we see a charge separation. That means, so here it is the arrow that is drawn here is for the positive x direction. So ions are moving in these directions, and with the velocity, electrons are exactly moving in the opposite direction. So what does it mean? This leads towards the charge separation. So obviously electrons and ions will go in opposite directions. That means that there is an electric field that will be set up, and ions will try to move across this electric field, and electrons will try to oppose this electric field, right. So the main important point is that the magnetic field being inhomogeneous allows charge separation, right. So this is the important point. So the magnetic field being inhomogeneous allows charge separation, and the velocity with which these particles will travel is generally called as the gradient drift velocity. So the gradient drift velocity can be more conveniently written as, let's say, V del B. Let's say there are a few more points. So plus minus V perpendicular RL divided by 2 BZ dou BZ by dou Y along x cap. Now for the given configuration of having the gradient along the y direction, for, let's say, the gradient is along, so the del B is in this direction, and B being just one component is in this direction. Right. For this configuration, the particle trajectories will look something like this. This is for ion, and this is for electron. So electrons, so what did I say? Ions, yeah, ions, okay, yeah. So here we made a mistake. According to the signs, it will be positive x direction for the electrons, and so this should be electrons, and this should be ions, right. So this is ions and electrons. Now what is the most important conclusion about the gradient drift velocity is that this separation of charges leads to something called as a very important aspect in magnetosphere or magnetospheric physics. Leads to something called as the planetary ring current. Okay, we will see how exactly, and what is the importance of this planetary ring current. So this planetary ring current is a very important aspect of space physics. I hope we can make some connection between the gradient drift velocity and the planetary ring current, right. So this was something about the gradient drift velocity. Generally what happens the gradient drift velocity can be more suitably or simplified in a more general form as, so V del B is mv perpendicular square divided by 2bz, or so V perpendicular, V del B is mv perpendicular square divided by 2q times B cross del B divided by BQ. So, now for the given direction of del B and for the given direction of B that we have taken, this form will again reduce to the same equation that we have derived earlier, or this can also be written as W perpendicular. Perpendicular is the perpendicular kinetic energy divided by Q times B cross del B divided by BQ, right. So, this simply implies that the velocity is perpendicular to both B as well as del B. For the case of Earth, the velocity will be in an equatorial plane along the longitudes. Okay. Now, so one very important understanding about the magnetic field vector B is that we know from the Maxwell equations that del dot B is equals to 0. So, what does it mean? The first thing that comes to your mind is that the magnetic field monopoles would not exist. That means the magnetic field should always, so one very important understanding from this is that the magnetic field should always converge and diverge. Converge at the, so if you take a simple bar magnet, let us say, if you take a simple bar magnet, the magnetic, let us say this is north and this is south, right. So, you will always see that magnetic field lines will always be like this for a bar magnet, right. So, one thing that you notice is that the magnetic field lines are converging and diverging at the poles. So, the direction of magnetic field, so what is the direction of magnetic field? For this, let us say direction of magnetic field is the direction along which unit north pole will travel. So, that means the direction of magnetic field is from north to south, right. So, for the case of Earth, the magnetic field lines diverge from the south pole, which is geographic. That means they will diverge from the north pole and they will converge to the south pole. So, this is the direction of the magnetic field, right. Now, what you see from this figure is that del dot B is 0, of course. The magnetic field lines converge and diverge at the poles. That means the strength of the magnetic field is maximum at the poles and its minimum, or it varies as a function of r. So, if you simply take a dipole magnetic field, if you the dipole magnetic field will look something like this. The radial component Br is mu naught by 4 pi 2m by r cube cos theta, and B theta is mu naught by 4 pi 2m by r cube sin theta. So, let us say, so what does it mean? It means that the magnetic field depends on the value of r. So, for different distances the magnetic field will be different. So, it means that the magnetic field, any realistic magnetic field that you find will always have a gradient. It's not possible that you will have a uniform magnetic field. Let us say, for example, it may be possible, but over a very limited space, if the magnetic field lines are extending from infinity to infinity, somewhere in between you may find magnetic field lines which are parallel and the magnetic field being uniform. But in all other cases, the magnetic field lines are always curved, and they are curved, let us say, between 2 points, between one pole and between the other poles. That means the magnetic field lines are always curved. So, what does it mean? So, the gradient of the magnetic field B is always associated with a gradient and a curvature. Curvature of the magnetic field lines, right. So now what we have seen is that the magnetic field, due to its gradient, gives away what is called as the drift velocity, curvature drift, sorry, the gradient drift velocity. We will also see that if the magnetic field, let us say if the magnetic field is assumed to be this curved magnetic field has a curvature, radius of curvature, let us say is assumed to be RC. Now, a particle, it is a charged particle, will gyrate across this magnetic field line, right. Now, as it gyrates, it also experiences another force in addition to the force that is created by the magnetic field. The additional force can be called as the FCF. What is FCF? FCF is the centrifugal force which acts away from the center of the radius, center of the curvature, right. So, due to the additional force FCF, we can also find out a drift velocity which is called as the curvature drift velocity. That means any realistic magnetic field will always be inhomogeneous and its magnetic field lines will always be curved, right. That means, if you see, for example, if the magnetic field is stretched over a very long distance, then it may be possible that this magnetic field lines are parallel over certain spatial distance, but otherwise the magnetic field lines are curved. So, if the magnetic field lines are curved, it will give away what is called as the curvature drift velocity. Now, the particle is of course gyrating parallel, the particle's velocity parallel to the curved magnetic field lines is taken as v parallel. Now, we again use Vr is now the curvature drift velocity is again F cross B by B square. Now, F is the centrifugal force, is the centrifugal force which can be written as, let us say, FCF is m V parallel square divided by RC. Right, which will act across RC. So, V R, the centrifugal force, can be 1 by q times m V perpendicular square divided by RC into RC cross B divided by B square. Or we can write the unit vector RC as RC bar divided by mod RC, right. So, in that case, we can write the curvature drift as 1 by q m V parallel square divided by RC square B square times RC cross B, right. So, this is the drift that the particle experiences as it travels across a curved field line, right. So, now the drift velocity due to the gradient in the magnetic field is V del is written as m V perpendicular square divided by 2q times B cross del B divided by BQ. So, this is again, so any realistic magnetic field should always have these two velocities associated with it. That means any particle which comes across a realistic magnetic field will always experience these two these two drift velocities. So, these two drift velocities, let's say what do you see? You see that the drift velocity due to curvature. So, Vr is perpendicular to RC, of course, and B, and V del is perpendicular to B and del B, right. Let us say, for example, we put the example of the earth. So, let us say if the earth is like this. So, this is the geographic south pole and this is the geographic north pole, and the magnetic field lines will look something like this, realistic magnetic field lines. Right. So, the geographic north pole is actually the geomagnetic south pole, and geographic south pole is actually the geomagnetic north pole. So, the magnetic field lines should look something like this. The direction of these magnetic field lines should look something like this. Now, if you want to understand the formation of ring current, let us define the directions. Let us say, so this is if this the curved magnetic field line is like this, the radius of curvature is of course in this direction, right. Now, the gradient of the magnetic field is in this direction away from the equatorial plane, let us say, and the original magnetic field is in this direction. This is the B and this is del B and this is RC. This is the RC cap. Right. Now, so the possible direction for the drift of the velocities, the curvature drift should be perpendicular to RC and B, right. So, it should be along the x direction, and the gradient drift should be perpendicular to B and del B. So, it should be along the x direction, right. So, that means that when the particles come, let us say when the plasma particle come, due to this the gradient drift and the curvature drift, this will lead into charge separation. That means electrons will go in the positive direction of positive x direction, and ions will go in the negative x direction. That means electrons will go to, if the now the earth is revolving from west to east, right. Yeah. So, sun is in this direction, this is the sun. So, electrons will go towards the dusk and ions will go towards the dawn. So, this eventually creates charge separation, and this charge separation will produce what is called as the planetary ring current out nearly 6 to 8 RE. It will be very strong current in the sense that its magnitude will be of the order of several millions of amperes, right. So, we will talk more about this ring current and its effects in subsequent classes. But however, it's reasonable that you combine the drift velocity due to the radius of curvature and the drift velocity due to the gradient, and you call this as the total drift velocity, V total. So, the idea is it is not possible to have drift velocity. It is not possible to have drift velocity only due to the gradient, because the gradient in the magnetic field imposes that there should always be a curvature. So, any realistic magnetic field should always have the curvature as well as the gradient. So, that then we define the total drift velocity of a particle which experiences a magnetic field. That means any magnetic field will throw the gradient part as well as the curvature part. So, we can write this as it is. I mean, we can combine this drift velocities as it is, which is mv parallel square divided by rc square b square times rc cross b plus m v perpendicular square divided by 2q b cross del b divided by b square. B cube it is, right. Or we can take a particular geometry and combine them in a more convenient or in a more suitable form. So, this is the total drift velocity that a magnetic field will offer a charged particle. So, this drift velocity depends on the mass and depends on the charge and of course, depends on the magnetic field. So, there is another more important way to add these two drift velocity components by taking a cylindrical geometry into consideration. Let us see we can do it in the next class.